Okay, this is 11.3, the dot product of two vectors. It looks like multiplication, but it's not. When you got vectors and you got a little dot between them, that's a dot product. And you multiply your x's together, u1 times v1, then you add, and then you multiply your y's together. So it's a very simple formula. If you got 3 dimensions, you multiply your x's together, multiply your y's together, multiply your z's together, and then add them all together. Okay, let's take a look at number 3. U is 3, 4. And vector V is -1, 5. And we want to find dot product of U and V. We want to find dot product of U and U. We want to find the magnitude of V squared. Dot product of U and V times V. And dot product of U and 3V. So the dot product of U and V, we're going to multiply the x's together. So I got 3 times -1 plus, and we'll multiply the y's together. 4 times 5. 3 times -1 is -3. 4 times 5 is 20. 20 minus 3 is 17. Dot product of U and U, that'd be the vector 3, 4, and 3, 4 again. So you multiply your x's together, 3 times 3. Then you multiply your 4's together, the y's, 4 times 4. 3 times 3 is 9, 4 times 4 is 16, which gives us 25. Now the magnitude of V. We're going to have the square root of V, which is -1 squared plus 5 squared. And all of that will be squared. Square root and the -1 squared plus 5 squared is just the magnitude, what's inside. Well, the square root and the second power are going to cancel each other. -1 squared is 1, 5 squared is 25, that gives us 26. Now, order of operations still holds true. Since we got parentheses, we're going to do what's inside the parentheses. And we got the dot product of U and V, which we found in part A, which is 17. And then times our vector V. So V is -1, 5. Treated like a distributive property when you got a number out in front of the vector. 17 times -1 is this -17. 17 times 5 is 85. Then that'd be your answer. Now over here, we're going to have our vector U, which is 3, 4. And dot product. And then inside of parentheses, we're going to have 3 times the vector V, which is -1, 5. Again, we do what's inside the parentheses first. Three times -1 is -3. 3 times 5 is 15. Then our dot product, we multiply the x's together. So 3 times -3. We'll multiply the y's together. 4 times 15. This is -9 plus 60, which gives us 51. I guess we could do number 9. That is a mixture. Yeah, 9 would be good. It's in 3 dimensions. It's also written as IJK. U is equal to 2I minus J plus K. And V is equal to I minus K. The J is missing here. So what? 0. So that's 0J. Then minus K. I see that in Calc 3 a lot. People, the 0 being missing, they tend to overlook the 0. You can't forget that. Now A says we want to find dot product of U and V. So we're going to multiply the x's together, the number that's in front of our i's. So we've got 2 times 1 plus, then we'll multiply what's in front of our j's, the y's, -1 times 0. Plus, then we'll multiply what's in front of the k's, our z's. So 1 times -1. 2 times 1 is 2, -1 times 0 is 0. 1 times -1 is -1, 2 minus 1 is 1. B, got dot product of U and U. So we got 2I minus J plus K. Dot product that in itself. So multiply what's in front of the i's together, the x parts, 2 times 2. We'll multiply what's in front of the j's, our y part, -1 times -1. And we'll multiply what's in front of our k's, 1 times 1. 2 times 2 is 4, -1 times -1 is 1, 1 times 1 is 1, which gives us 6. What is this equal to, by the way? The
You mean just U squared?
yeah, but more than that.
I don't quite. You mean like R or something? Or you having two lines at different times?
I mean, physics-wise. I don't really know myself. I'm asking you because
U is just nothing. It's basically just a letter over A.
No, I mean when you take the dot product of itself in terms of physics, what does that represent?
What it represents is you have. I think you already explained it, but you have your graph.
Mm-hmm.
And in physics, you can make one graph do whatever you want for anything.
Uh-huh.
But basically, let's say you have this is your U right here. That's your U.
Yeah.
And let's say you stack another U on it. But you now have an extra U at the exact same length, the exact same distance, the exact same angle. Therefore, you're trying to find what's the length of that, which is what's in between. It's basically you're finding a triangle.
Oh, okay. I didn't know. I haven't had physics for 35 years. So, I mean, I know how to use a formula. It's pretty mindless. But yeah, some of my physics knowledge is weak. I didn't know what taking a dot product of a vector with itself gave you. But you see it a lot in books, so I assume it meant something. Okay. So here we're going to take the square root v 2 negative 1 1. So 2 squared, negative 1 squared, and 1 squared. Second power. Square root and second power cancel each other, and that gives us 6, which matches what we got here. Is that v? Let's try it again. Wondering why that matched. My eyes are no good. What's v? So 1 0 negative 1. 1 0 negative 1. Again, the square root and the second power cancel each other. 1 squared is 1, 0 squared is 0, negative 1 squared is 1. That gives us 2. D. We got the dot product of u and v times v. U is 2I minus j plus k. And v is I minus k. Times v, which is I minus k.
We already did that one.
Did we?
I mean, we already, no, we didn't. We already did that first part, which equals 1.
Does that equal 1?
Whatever you have right there, which is just.
Yeah. So 1 times I minus k, which, like you say, gives us I minus k. Yeah, I guess you've seen enough of that. Now here is a theorem to find the angle between two vectors. So theta is the angle between two non-zero vectors, u and v, where theta is between and including 0 and pi. Then cosine theta is equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Last chapter?
Yeah, last chapter.
Yes, the last chapter we covered. Yeah. We got one more section to cover, and then we're done with the material for the course. Kind of sad, huh? Okay. And it says find the angle theta between the vectors in radians and in degrees. So we want to use this. So the dot product of u and v, we're going to multiply the x's together, 1 times 2, plus multiply the y's together, 1 times negative 2. And I'll do the bottom part just for fun. But what's this give you? 0. Yeah. So the magnitude of u, we're going to have square root of 1 squared plus 1 squared. Square root of v is 2 squared plus negative 2 squared. Don't need to plug this one into the calculator. Hopefully the next one I pick won't come out like that. Cosine theta is equal to 0 is what in radians? Between 0 and pi. Pi over 2. And in degrees, it's 90 degrees. I'm assuming that one doesn't come out nice. Let's look at number 17. U is equal to 3i plus 4j. And v is equal to negative 2j plus 3k. If theta is an angle between two non-zero vectors, u and v, where theta is between 0 and pi, including 0 and pi, then this is true. Does it say anything about having to be in 2 dimensions? No. So we're just going to use the same formula. Okay, so our dot product, we multiply what's in front of our eyes. First one has an eye, but second one doesn't have an eye, so that goes to 0, drops away. Actually, write it. 3 times 0. Multiply what's in front of our j's. So we got 4 times negative 2. And multiply what's in front of our k's. We got 0 times 3. Over the magnitude of u, which would be 3 squared plus 4 squared, k's missing there, times negative 2 squared, and the i's missing, of course, plus 3 squared. Zeros drop way up on top. We got negative 8 down the bottom. 3 squared is 9, plus 4 squared is 16. 9 plus 16 is 25. Square root of 25 is 5. And negative 2 squared is 4. 3 squared is 9. 4 plus 9 is 13. So we got this right here. This is what I was hoping for, because that's definitely not in the U circle, is it? There's no square root of 13s. So we take arc cosine or inverse cosine, however you want to think of it. Now, the instructions say to put in radians and in degrees. Technically, we just solve for theta, and this is an exact value, isn't it? If you're going to use this in the further calculation, you'd want to leave it in this form. I'm going to plug in the calculator because that's what the instructions imply. You'd have to put in both. The instructions want you to do it both. A is radians, B is in degrees. Yeah. Okay, so I'll do radians first. I'll go to mode, make sure I'm in radians. I am. And second cosine, -8, divided by, and I'll put parentheses around the bottom, because there's more than a single number down there, 5 square root of 13. Doesn't really specify, I'll take 2 decimal places, 2.03. To put it in degrees, I would go to my mode, change it to degrees. On your calculator, you got a nice feature, a history. So if you do second enter, it brings that back your previous entry. And then you press enter again, and that's 116.34 degrees. And those will be our two answers. Questions on that? Now this was in the bottom of one of the pages in the book, kind of important information, but they don't really highlight it. If you see up here at top, of course, there's the opposite direction where theta is equal to pi, and cosine theta was equal to -1. But if you got this right here, where the dot product is less than 0, this tells you how big the angle is. Now I had to search my own memory when I was putting this PowerPoint together. What kind of angle is that? Obtuse. Yeah. Now here, if your dot product is equal to 0, and we're going to see it's officially written out soon, but that means that you got a 90 degrees here, perpendicular, or in vector notation, it's called what? Orthogonal. They didn't talk about that in physics? Really? Technically, it's incorrect to say perpendicular, but that's the way we think of it. And then if your dot product is greater than 0, we got this kind. What kind of angle is that? Acute. Yeah, acute is less than 90 degrees. Obtuse is greater than 90 but less than 20. And then same direction, theta is equal to 0, cosine theta is equal to 1. Okay, let's take a look at number 27. Normally, I don't like to show these type of problems. They're so bizarre that you never really use it, but I figure we'll have the time. Now this says, vertices of a triangle given, determine whether the triangle is in a acute triangle. What's an acute triangle? Do you remember that? What? Yeah, all of the angles are less than 90. An obtuse triangle, one is greater, yeah. So one is obtuse, isn't it? What does the other two have to be then? They have to be acute. So one obtuse, two acute. Or a right triangle, which you know what a right triangle is, 90 degrees, sharp corner. So, to understand the relationship between these, let's go ahead and yeah. Yeah, that's why I picked this one. Because what's a z in all of them? 0. So we don't even have to consider that. Yeah, it would be painful if you had to watch me actually try to do 3D. Okay, so 1, 2 would be right there. 0, 0 would be right there. Negative 2, 1 would be right there. Of course, I don't draw very well. So, let's consider 1, 2, 0, 0, 0, 0. And we're going to look at the angle between them. And that'll help us figure out, what's going on with it. Now, since they're all, or this is 0, 0, 0, then our vector, if we subtracted our points, would just be the other one, wouldn't it? So if I looked at 1, 2, 0, which is right here, and I looked at 0, 0, 0, then my vector there would be subtracting them. So it'd be 1, 2, 0. Now for my other one, it's negative 2, 1, 0, and 0, 0, 0. And again, you take your terminal minus your initial. And this vector would give us negative 2, 1, 0. And we're trying to find that angle between them. So we got 1 times negative 2 plus 2 times 1, which gives us 0, which according to our rules over here, the dot vector equaling 0 tells us it's a 90 degrees. So if that's actually 90 degrees, as it looked, this would be a right triangle. Does that make sense on that? We don't need to go any further. Since it's got 90 degrees there, then we know that's a right triangle. Those will never be on a test. Just, you like those?
Yeah. As long as we don't have that extra coordinate.
I guess I like problems that seem like there is reasonably a real world application for. I can't imagine you'd ever doing that in a real world sense. That's why I don't like those. Okay. We already talked about the perpendicular versus the orthogonal. Again, vectors are considered orthogonal, and vectors u and v are orthogonal when the dot product is equal to 0. Here's an alternative form of the dot product. The dot product of u and v is equal to the magnitude of u times the magnitude of v times cosine theta. And I don't know why, but books tend to leave this off, so I made this up myself. The vectors u and v are parallel if there's a scalar value c such that the vector u is equal to c times vector v. And we'll see what that means. A scalar, a constant, a number. I mean, it makes sense. I just don't know why they never really write it out. Let's take a look at number 21. I think that is I'll bring up the look ahead here in a little bit, but I think there is one on Thursday. And the instructions say determine whether u and v are orthogonal, parallel, or neither. To determine if they're orthogonal or perpendicular, you find dot product of them. So dot product of u and v is going to be 4 times 1/2 plus 3 times negative 2/3. That gives us 4 over 2, or 2. Those 3's cancel, minus 2, which gives us 0. Which implies that they're orthogonal. And in theory, they if they're orthogonal, they can't be parallel, right? I took a college geometry class. I was so I took it twice actually. Didn't do well on it the first time. I learned my lesson there at Wichita State because I arrived late, or not late, but 5 minutes before class started, the first day of class. And class is full. I had to sit over on the side. And, you know, kind of once you stake your territory, people don't move anymore at that point. Yeah. And, or no, where did I have? No, I had to sit in the middle. And you think, would it be prime real estate there? Well, he taught the entire class standing in front of whatever he was drawing. So he's drawing these geometric shapes. I never could see any of it. Like, all I could see was his back. And a lot of professors at Wichita State, you don't ask him to move to the side so you can see. And they don't like questions, period. And got a D in that class. So that next time I took it, then yeah, college geometry. Well, it's a step beyond high school. The next time they offered it, I'd arrived 40 minutes early, I think, for class. I staked out my area. I knew exactly where to sit so I could actually see the board. Same professor, yeah. He right. And it's amazing. I could actually understand the material when I could see him do the geometric instructions instead of his back. Did real well then. But that class just got confusing anyway. It introduced projective geometry. You ever hear that? In projective geometry, there is no parallel lines. Yeah. Because in reality, is there parallel lines? Yeah, because if you look at a road as it's going away from you, the lines are going together, aren't they? I think what really threw me in the class when he drew a circle and said this is a line. I was so lost at that point. Just whatever you say. We pass this time, so I don't have to take this again.
Anybody taking
I liked him. He was he taught forever. Professor Richardson. He was like a icon at Wichita State. Boy, he hated cell phones. Hated them with a passion. One time one went off, and the person shut it off, immediately. But boy, we listened to a 20-minute lecture about cell phones, and one went off again during class, and I think it was during a test even, if I remember right. And whoever it was would not answer it. It just kept going off, and just like, I don't blame him. He probably failed you as much as he hated his cell phones. Yeah, exactly. I guess that's what they figured. Okay, same instructions. Well, again, the orthogonal part, we do the dot product, see what it gives us. Multiply what's in front of our i's. We got 0 times 1. There's no I in this one. Multiply what's in front of our j's. So we got 1 times -2. Multiply what's in front of our k's, which is 6 times -1, which gives us -8. So not orthogonal. The what? Oh.
Yeah.
Now, in terms of the parallel, it's probably easier to write it in the other notation. Let's see, there is no I, so that's 0, 1, 6. And B, be 1, -2, and -1. Now, an example of a parallel. 2, 3, and 4, 6. Reason why this would be parallel is I could factor a 2 out of this, and then this vector looks like this vector. So if you can factor a number out and then those vectors are the same, that means there's parallel. I got a 0 here, which causes me a huge issue right there. It don't matter what I factor out, I am never going to get these match. So these are not parallel. So they're neither. Hopefully the next one's parallel so we can actually see an example out of the book on it. Okay, number Is number 25 parallel? No. So it's not going to be doing me any good. I think number 22 might be. Let's look at 22. Some of them I can see easily. Some of them I think it through. Okay. And I'll write in this notation. So I got 1, -2. And 2, -4. Yeah. Definitely not orthogonal, right? If I multiplied -1/3 times 1, then multiplied times 2, I get -2/3. If I multiplied -1/3 times -2, that gives me +2/3 minus 4. Let's see, 2/3 times -4, -8/3. That's -10/3. So no. Now here's the challenging part though. The definition doesn't say take a number out of each one of these, just out of one of them. If we follow the definition strictly. So question is, what can I factor out of the? What more can we factor out of the top such that I have a 2 here? What? Because the formula does not say that you can factor out of both sides, strictly speaking. See, it just has C on one side. Well, let's go backwards first. So multiply the negative 1/3 through. Now, my goal is to factor something out of the top, and I'll focus on just one item, specifically the x. And so I want to bring something out in front that would leave me a 2 here. So I have to think about this myself. Is it boy, it's been a long day. -6? Okay, factor a -6 out. Let's see what that does. No, that wouldn't work, would it? So that my -6 works? It's backwards, I think. So 2 times what equals -1/3? -1/6? Yeah. I just had this backwards. Okay. So I'll factor out a -1/6. And -1/6 times 2 gives me -2/6 or -1/3. And -1/6 times -4 is a +4/6 or 2/3, which is that. So that's what we would factor out. So this would be our C from our definition. So the answer here is yes, they would be parallel. Why is that? Why would that be important just to factor it out one of them? What does that number give us? Yeah, because remember when we were graphing these, you'd have like a I here, and then we looked at 2I. That made it twice as big, right? So again, having numbers just in front of one of them gives you a perspective on what it does, how they compare. They're definitely parallel, but one of them is 1/6 less, and negative would be going where? Yeah. Okay. Take a look at number 19. This is the alternate form of the dot product. Okay. Magnitude of u is equal to 8. Magnitude of v is equal to 5. Angle between them is pi/3. So our dot product is equal to magnitude of u times the magnitude of v times cosine theta, where theta doesn't say it, but theta is the angle between them. So I have 8 times 5 times cosine of pi over 3. H times 5 is 40. Cosine of pi over 3 is what? 1/2, which gives us 20. Now here's some direction cosines. And this is if you going on to Calc 3, if you're going on to Calc 3, this is using Calc 3. And you see these angles right here. If x is this way, y is this way, z is this way, then this vector here coming from the x-axis, that's alpha, so that gives you that angle. From beta, that's from our y-axis. And then coming down from our z-axis is, oh boy, is that gamma? Yeah, well, yeah, I think it's gamma. I don't deal with the Greek letters that much, but that give us that. That we're going to see in, you're going to see in Calc 3 that that's another way to represent like a point. It's another coordinate system, basically. Spherical. Anybody ever hear of spherical? Yeah. Anyway, finding those angles. Now, one thing to note here is up here we got our dot product of v and the vector v and vector I. That gives us our v1. So we got 1, 0, 0, and basically your first part right here. So that's why this is v1, and along the same lines, this is v2 and this is v3. Because we would take the dot product on v2 with the j, which is 0, 1, 0. For v3, we take the dot product with k, which is 0, 0, 1. Remember our unit vectors? But anyway, that's how they came up with those formulas. So, number 31. Vector u is equal to I plus 2j plus 2k. And the instructions say find the direction, cosines, and angles of something. They got that wrong, but that's okay. What's wrong with the directions? What is a lowercase u? No. Vectors are bold. We have no clue what lowercase u is. So, but since they made this all bold, we assume it's a vector. Not to be picky. Okay, so u is equal to this. Come back to here. All of these involve the magnitude, don't they? Okay. Now, See these here? These are the direction angles of vector v. The fact that we're using u does not matter, does it? So just want to point out, doesn't have to be v, doesn't have to be a, it can be b, it can be z, zeta, whatever. So 1 squared plus 2 squared plus 2 squared. Long day. I shouldn't have to do that. 3. So that'd be our magnitude. Now, whatever's in front of this is going to be our u sub 1. This is our u sub 2 and u sub 3. So cosine alpha is equal to u1 over the magnitude of u. So we're going to have 1 over 3. And alpha would be inverse cosine of 1/3. Now our next one is beta. So we've got cosine beta is equal to u sub 2 over the magnitude of u. U sub 2 is 2 over 3. Or beta is going to equal to inverse cosine of 2/3. And cosine, what did I say, gamma? Boy, I can't draw that. It's equal to u3 over the magnitude. So that'll be 2/3 also. Or gamma is equal to inverse cosine of 2/3. I won't actually plug those in, but you plug those in your calculator, I'd give you your results. Does that make sense on how to get those? Okay, definitions of projection and vector components. Let u, the vectors u and v be non-zero vectors. Moreover, let the vector u is equal to the vector w sub 1 plus vector w sub 2, where the vector w sub 1 is parallel to vector v, and the vector w sub 2 is orthogonal to v, vector v, as shown in the figure I didn't copy. W1 is called a projection of u onto v, or the vector component of u along v, as denoted by W1 is equal to projection along v of projection of u onto v. And 2, W2 is equal to u minus W1 is called a vector component of u orthogonal to v. What's this used for in physics? Do they not cover projections?
No, I think they did.
No. Now here is our official definition. The projection using the dot product. If u and v are non-zero vectors, the projection of u onto v is given by this formula. So we got dot product of u and v on top over the magnitude of v squared times the vector v. Okay, so let's take the what? Oh yeah, sub B there. Oops. Yeah, I didn't think I was going that far. That's weird. Okay, so let's take a look at the next problem. Let's take a look at 37. U is equal to 6, 7. V is equal to 1, 4. First thing it has to find is find a projection of U onto V. If I come here and read this, projection of U onto V. This one has U first and the V second, doesn't it? This one has the U first and the V second. How about if this said projection of V onto U? What would I then need to do? Yeah, swap the U and V. Now, in some cases, it doesn't matter, but other cases it may. You know, like the dot product doesn't matter how you do it, right? But anyway, it matches perfectly here. So. Dot product. Magnitude squared times V. So I take 6 times 1 plus 7 times 4. In the bottom, we'll have the square root V, which is 1 squared plus 4 squared, that squared, times V, which is 1, 4. Like I say, that's 28 plus 6, 34. On the bottom, we got the square root and the second power cancel each other. And 1 squared is 1, 4 squared is 16, so it gives me 17. That works out nice. Which gives us 2. Which gives us 2, 2, 4. 2, 8. If I were to multiply through. You notice that it's 2, this comes out as a number, always, times our vector v. So it's always some kind of magnitude of v, a distance applied to it. Questions on that part? Okay, second thing they're asking for, find a vector component of u orthogonal to v. So, vector component of u orthogonal to v. Now look at this right here. Vector component of U orthogonal to V. That's a second formula here, isn't it? Which means we need U minus W1. U was something 6.7 minus, and W1, notice here, is the projection of U onto V. Projection of U onto V is what we just found right here, isn't it? So this is our W1, which would be 2.8. Six minus 2 is 4, 7 minus 8 is -1, and that would be our answer. One thing that people have trouble with in Calc 3 is when these letters start changing. People get so used to, well, U and V, it has to be in that form. And unfortunately, if you look in the book, he doesn't get very adventurous there, does he? Like if I look at this, UV, 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 UV. They're all UV. Been better if you'd flipped them around, something like VU, AB. So you're thinking much more than just blindly plugging them into the formula. Now I don't have much trouble with this because I'll write it out like this, and then I'll see what it maps to. So that if they were flipped around, if this was flipped around like this, then I could change the formula accordingly. Questions on that formula? Formulas. Last definition of work, the work W done by a constant force F as its point of application moves along the vector PQ is one of the following. Here's a projection form and here's a dot product form. So, do you use those in physics? Is it? Oh, it is. Well, we're not going to do any problems on this. There's none on test on that form, but I wanted you to see it. So if you were to go into physics, and that's meaningful in physics, some of the things that you see in, and I may have mentioned this, I'm getting old, I repeat myself. There was some topic covered in Calc 3, pretty complex topic. And I went to my friend at Cali. He got a PhD in mechanical engineering, and I asked him, well, where do you use this in real life? Because I want to talk to the students and tell them, where they're going to be using this at. So we don't. We do it an easier way. So some things you see from a definition, a formula standpoint in the book may not be what you actually do in real life. Questions, maybe? Well, we're done with that section. I'm not going on 11.4 because I don't want to finish up too early, so let me go over the look ahead. If you're struggling with something, use this time to your advantage. I really don't have an exciting life. Now that the election is over, I feel like this real void in my life, My part is over. Not what happens. And
the amount of votes is more than the amount of voters registered. How is that possible?
I was reading that on Facebook, and they did a fact check, and it wasn't true what they said. The numbers were like from the 2016 they were comparing. But still, I'm not sure if I really believe the number of registered voters versus how many they say voted. I cannot believe 90% of people are getting out there and voting in Wisconsin. So it's just, well, that don't seem quite right, and it's just like, but the thing of it is, I think both parties do it. I think just this time it came back and bit the Republicans. Okay, so our look ahead. Today we did 11.3. We got one more section, which we'll do next class, 11.4. The test will be a week from today over chapter 11. And so again, work problems out of the book, get comfortable with those. The following week, 11.17, there'll be a makeup test day. And then 11.19, I'll come in, I'll answer any questions you have. Best thing to study up for the final exam is the previous test. Now, the final exam is not going to be this real hideous thing. It's going to consist of probably 10 to 15 questions, just because I got to get it graded and get it in pretty fast. They were emphasizing that in an email they sent out earlier this week. They said, there's no procrastinating on your grades this time. We have to have them in. So I suppose is that right before Thanksgiving? Is it? That's probably why they sent out the little email, because I think it has to be in like I don't know when. But anyway, it had to be pretty quick. Any questions on the look ahead?
So, will you be going over like some stuff that you on the test?
No.
I mean, on the final.
No.
Oh.
But I will answer any questions you have. Like if you look back at your old tests and you don't remember how to work something, use this time to your advantage. I'll answer any questions you have and so forth. Well, we'll go ahead and stop there. Like I say, if you have questions, stick around. I'll help you. But otherwise, we're done.